Welcome everyone. Today we will discuss the last part of oxidative addition, that is the radical mechanism. We have seen in the last two classes oxidative addition by concerted mechanism and oxidative addition by SN2 mechanism. Of course, obvious other option that is left is the radical mechanism. Is it possible? Of course, it is possible. Radical mechanisms are possible for a number of cases, specifically those substrate which will not undergo SN2 reaction, for example, that very easily, then radical mechanism is one of the most viable option. Now, how are we going to know that which is the radical mechanism? Of course, there are few experiments which we can do to be sure. As the name suggests, radical mechanism will not get reproducible kinetics data that we have already understood while we were discussing the SN2 reactions. So, non-reproducible kinetics data will be one of the proof in favor of radical mechanism. Of course, other techniques that we can utilize in this case is to use radical traps. If we use radical traps and if a radical mechanism is prevalent, then what we will see, the reaction will either completely shut down or at least considerably shut down in case of the radical reaction in presence of the radical trap. In addition, we can have different initiator or sensitizer initiator, mainly oxygen, light as initiator or other initiator we can use for such reaction. Most importantly, if you look at the stereochemistry point of view, if a radical mechanism is happening, the stereochemistry of the let us say halide, the Rx where the oxidative addition is occurring, stereochemistry will be lost. In the concerted mechanism, we have seen the stereochemistry is intact. So, if you were starting with a Rx with which the oxidative addition is going to happen and the Rx is having a chiral center in it, the chiral center will remain intact if it is a concerted mechanism. So, the chiral complex will give a chiral final product, organometallic product for concerted mechanism. If it is a SN2 reaction, as you know, it is a backside attack. So, the inversion of configuration will be observed, but if it is a radical mechanism, we will see that the chiral center will be racemized. So, the product, final product will be a racemic product from starting a chiral Rx species. So, these are the characteristics. Let me try to write down very briefly about these characteristic. As we have discussed, the characteristic of a radical mechanism will be loss of stereochemistry, chemistry at Rx, if Rx is having stereochemistry, irreproducible reaction rates. Okay, the fluctuation will be there, inhibition by radical traps, finally, we can also expect acceleration by oxygen, light, other initiator, etc. Right. Now, of course, for any radical reaction, we can expect two type of mechanism. One is the non-chain radical mechanism, another is the chain radical mechanism. We will discuss briefly the non-chain radical mechanism, where we will see the reaction starting material usually is an odd electron one. Often we see that for let us say 17 electron complex, 17 electron organometallic species will gives rise to a oxidative addition that is undergoing a radical mechanism. Let us take one of the real life example right now. So, we are discussing non-chain radical mechanism. Now, what could be better complex than cobalt for a odd electron species? If you do the electron count, you will find that this is a 17 electron species. It is a D7 cobalt 2 plus, do the electron count, it will be D7. Now, these species, 2 of these species will react with Rx to give you RCO CN5 3 minus and XCO CN5 3 minus. Now, this Rx, if you are varying different Rx, like say iodide, bromide, chloride, rate constant for the iodide will be faster than bromide, then your chloride and so on. Again, this further proves that it is a radical mechanism. If iodide is faster than bromide and then chloride, this suggests that it is a radical mechanism. Therefore, this is again consistent with radical abstraction. Right. Now, of course, it is a non-chain radical, it happens in a stepwise manner. So, the cobalt complex, which is the 17 electron species, will react with Rx in a stepwise fashion. Let us write down the stepwise reaction mechanism. So, CO CN5 3 minus reacts with Rx, this is an abstraction step to give you X CO CN5 3 minus species, which is an 18 electron species along with R dot. Now, this another molecule of COCN5 3 minus will react with that R dot to give you so called radical coupling, and finally we will get RCO CN5 3 minus. Of course, this is again 18 electron species. So, what we have seen so far here, cobalt pentacyanide species reacts with Rx to give you X cobalt COCN5 3 minus along with R radical formation. This radical will combine with the cobalt, which is again it is a kind of a radical intermediate, it is a 17 electron species, to give you radical coupling overall RCOCN5 3 minus. Both these species are 18 electron in count. So, if you combine these two steps, overall we will have 2 molecule of the cobalt species reacting with Rx to give RCOCN5 3 minus plus XCOCN5 3 minus, right. So, this is how actually radical reactions are. You have seen the radical reaction before. The mechanism is rather straightforward. You need to generate the radical somehow. If your organometallic intermediate happen to be a radical intermediate such as 17 electron species, in this case we have seen the cobalt species. Previously, if you notice carefully, for the concerted mechanism and also for the SN2 mechanism, we were mainly discussing the 16 or 18 electron complex. Never really we were discussing an odd electron species like 17 electron species. But for radical reaction, either your starting material is having odd electron, or you have to create such atmosphere where odd electron is there. Okay. Now, we will take one of the example which is a 16 electron species to start with, but then it is undergoing a radical mechanism. In this case, what you need is a promoter or a initiator to initiate the reaction. So, 16 electron species will initially converted will be converted to a 17 electron species, and then that 17 electron species will undergo the radical reaction overall to give you the oxidative addition by radical mechanism. So, it is not necessary to have the organometallic species in a radical mechanism to have the odd electron like 17 electron to start with. We can start with an even electron organometallic intermediate, and then an initiator can initiate the reaction, it can do the job to promote the reaction, and then overall a radical reaction then follows. Let us take an example. Once again our favorite complex, this iridium complex, it is a 16 electron species. Now, let us say this is the species A. This species A will react with Rx. Let us say this is 4 for your SN2 substrate. Let us say tertiary butyl fluoride or anything you would understand that will not undergo SN2 reaction. Now, this will undergo the radical oxidative addition overall to give you iridium Rx species to give you the first form intermediate is the one which will have the initiator. Let me first draw the oxidative addition complex. So, a 16 electron species is undergoing oxidative addition overall to give you an 18 electron species, but in this case particularly we are emphasizing that the Rx is not the one where SN2 reaction will be easily done. Can this reaction go? Of course, it can go. A 16 electron species can undergo an oxidative addition via a radical mechanism, but it will not be a straightforward one. You need again a initiator. In this case, the initiator will bind with the starting 16 electron complex. Once again, the Rx that we are using, it is not a substrate where simple SN2 reaction will be possible. In such cases, let us say tertiary butyl fluoride, of course, there is no way you can get an SN2 reaction. What you can do to get the oxidative addition is to start with an initiator. Let me draw then. So, the A, the organometallic intermediate A will react with the initiator to give you initially iridium initiated species. Okay. Rest of the coordination remains same, and then the Rx will be the one which is getting involved to give you iridium complex where you will have X and initiator involved with it. Okay. Now, this intermediate will all other coordination then will react further with the R dot. So, the X is here, R dot is there, R dot will be replacing the initiator to give you the final this complex 18 electron complex, let us say this complex B. So, what we have seen, the A is binding with the initiator to give you iridium initiator complex, from where Rx will be combined with this to give you the first initiator X complex, the other coordination 4 coordination remains exactly the same, and then the R dot will replace the initiator to give you the 18 electron final species. Okay. The propagation for this reaction will involve the R dot. So, the propagation, let us say reacting with the initiator, okay, to give you R A. Now, R A will react to give you R A plus R X will give you R A X species plus R dot. That is how the reaction will propagate. So, once you have an initiator to initiate this radical mechanism, the reaction will take care itself, because the next step will be the R dot. That R dot will then react with A, again it will go and do the reaction to give you the reaction in a stepwise manner. So, what we have seen so far is two examples of radical mechanism. In one case, we have 17 electron complex, that is the cobalt species reacting, the 17 electron species reacting in a radical mechanism to give you first an 18 electron species, and then another radical gets generated. That radical will again react with the metal complex to give you two species. So, two equivalent of the cobalt intermediate was giving one equivalent of the cobalt R species and another equivalent of cobalt X species. Both of those species were 18 electrons when we have a 17 electron starting material. It is good to have an odd electron species for the radical mechanism, but it is not essential to have the odd electron species. In case of even electron species such as 16 electron species, the iridium species, the Vazquez complex we were trying to discuss, we need to have a promoter or the initiator to start kick the reaction. Once we have 16 electron complex converted to a 17 electron complex in presence of an initiator, the initiator will bind with the iridium complex, in this case Vazquez species, and thereby the next radical reaction will start off. Once the radical reaction is start off, you do not need the initiator anymore. The radical generated from the reaction will take care of the progression of the reaction. Okay. So, that is what is the radical mechanism. Of course, if you try to look at the radical mechanism, the standard characteristic for this reaction will follow as we are trying to discuss. The radical scavenger you can add. So, radical scavenger will be able to stop the reaction, we will not have a reproducible kinetics data, and if the Rx is having the chiral center, the chirality will be lost in the process. More importantly, if it is a tertiary halide, that will be reacting faster compared to the secondary halide. That is once again proving that it is a radical mechanism. If it is a SN2 reaction, you would expect the other way around, that means the primary will be reacting faster than secondary then tertiary. But for radical mechanism, you will see the tertiary halide will be the fastest. So, that is all for the radical reactions, or that is the conclusion for the oxidative addition reactions. To summarize oxidative addition, we have seen different types of oxidative addition over the last two classes, where we have seen oxidative addition by concerted mechanism. The Rx and the metal interact in a concerted fashion to give the cis product, and we have seen a number of examples for that. Subsequently, we have discussed the SN2 mechanism as much as you have seen in the organic reaction, SN2 similar to that organic reaction. In case of concerted mechanism, if the Rx is having chiral center, we will have the chiral center remained intact. For SN2 mechanism, we will have inversion in configuration, and for radical mechanism, we will have basically the racemization of the chiral center. So, essentially what we are seeing increasingly is the mechanism will depend on the type of Rx we are having. That is most crucial what type of Rx we are having, that will kind of determine the course of the reaction, and of course, the metal species that is involved in the oxidative addition will also be crucial to judging which mechanism is prevalent. So, it is a combination of the metal species and the Rx that will determine which mechanism will be followed. If you see, usually if you see that Rx, R and X after oxidative addition, if it is trans to each other, then most likely it is a SN2 or radical mechanism that is involved in it. If Rx is cis to each other, then most likely it is a concerted mechanism that is involved. And there are a number of examples that is there, where we can see the oxidative addition is the key step. Starting from, let us say, palladium complex, we have seen a number of reactions. Even 2010 Nobel Prize is given on the cross coupling reaction, where we have Heck reaction, aryl halide, let us say phenyl bromide or bromobenzene basically, reacting with a palladium 0 species to give you palladium 2 plus oxidation state, and the aryl and the iodide or halide is also interacting with the metal species. So, palladium 0 interacting with phenyl iodide, let us say, or iodobenzene or bromobenzene to give you palladium aryl or palladium phenyl and the halide species. So, both phenyl and the halides are attached with the palladium species. This is the first oxidative addition intermediate species. Then for the Heck reaction, we will see, we will discuss that olefin will interact with the palladium, and then insertion of that aryl intermediate will involve to give you the final product. This is one of the reaction that got Nobel Prize in 2010. Another famous reaction is the Suzuki reaction, which got the Nobel Prize, again shared Nobel Prize in 2010 with Heck. There we do see that it is again a oxidative addition that is happening over there. The first step is the oxidative addition, and then oxidative addition into, let us say, a different aryl halide or alkynyl halide or even alkyl halide, and subsequently we will see that oxidative addition intermediate will undergo transmetallation and then reductive elimination to form the product. Another reaction that actually also shared the Nobel Prize is the Nigisi reaction. Again, all these reactions 2010 got the Nobel Prize combined. So, Heck, Nigisi and Suzuki reaction, these are of very fundamental use of the organometallic intermediate, organometallic principle that we will be discussing shortly in the classes. So, in the next class, we will discuss the reductive elimination. Reductive elimination, as one can imagine, is the opposite of oxidative addition. Whatever is happening in the oxidative addition is the increase of electron count by 2. So, 16 electron complex is undergoing a product formation where 18 electron species is formed. Now, for reductive elimination, just to tell, if you take the 18 electron species, it will give you the 16 electron species. It is almost the microscopic reversible intermediate. So, till then, for the next class, we will see for the reductive elimination in the next class. Keep on studying, and if you have any queries, please let us know. Thank you very much.